Look up at the night sky. On a clear night, far from the city lights, you can see thousands of stars. Each one is a sun, much like our own. Many of them likely have planets orbiting them, just as Earth orbits our sun. For as long as we have been human, we have gazed at these distant lights and wondered what lies out there. This vast expanse, this cosmic ocean, has always called to us. It is a fundamental part of our nature to explore, to see what is over the next hill. Now, the next hill is another star system, and the desire to go there is as strong as ever. It is a dream woven into our collective consciousness, a longing to journey beyond our small blue world. The scale of the universe is almost impossible to comprehend. Our nearest stellar neighbor, Proxima Centauri, is over 4 light-years away. This means that even if we could travel at the speed of light, the fastest speed possible in the universe, it would still take us 4 years to get there. Using our current technology like the Voyager probes, the journey would take tens of thousands of years. The stars, for all their beauty and allure, seem impossibly distant. They are like islands scattered across an ocean so vast that a lifetime is not long enough to cross it. This cosmic speed limit, imposed by Einstein's theory of relativity, appears to be an unbreakable barrier, locking us within our own solar system. This fundamental limitation is what makes the idea of faster-than-light, or FTL, travel so captivating. It's a recurring theme in our stories, our myths, and our science fiction. We imagine starships that can cross the galaxy in days or weeks, allowing humanity to explore new worlds and meet new civilizations. The problem of interstellar travel is not about building a faster rocket engine. It's a problem of space-time itself. Albert Einstein's theory of general relativity revealed that space and time are not separate, static things. Instead, they are woven together into a single dynamic fabric called space-time. Massive objects like planets and stars warp or curve this fabric, and this curvature is what we experience as gravity. This insight completely changed our understanding of the universe. So if you cannot travel through space faster than light, what if you could move space itself? Imagine you are standing on a rug. To get to the other side, you could walk across it. But there is another way. You could ask someone to pull the rug towards you, bringing your destination closer without you taking a single step. This extraordinary concept is known as the Alcubierre drive. It was proposed in 1994 by a Mexican theoretical physicist named Miguel Alcubierre. What is fascinating is that he was not trying to solve a long-standing problem in physics or cosmology. He was, by his own admission, a fan of science fiction, particularly the television series Star Trek. He was watching the show and began to wonder if the warp drive depicted in the series could be made consistent with the laws of physics as we know them. He wanted to see if the mathematics of general relativity could describe a real-life version of the Starship Enterprise's famous propulsion system. Alcubierre sat down and worked through the complex equations of Einstein's theory. His goal was to find a solution that described a warp bubble which could transport a volume of flat, normal spacetime from one point to another at superluminal or faster-than-light speeds. He found one. He published his findings in a scientific paper titled The Warp Drive Hyperfast Travel Within General Relativity. The paper laid out the precise mathematical requirements for creating such a bubble. It described how spacetime would need to be compressed in front of the bubble and expanded behind it to achieve this incredible feat of motion. The publication of this paper sent ripples through the physics community. It was a serious, mathematically sound proposal for a technology that most people believed belonged purely to the world of fantasy. For the first time, faster-than-light travel had a foothold, however tenuous, in real science. To truly understand how the Alcubierre drive might work, we first need to get to grips with one of the most profound ideas in all of science, the concept of spacetime. Before Albert Einstein, we thought of space as a fixed, empty stage, an unchanging background where the events of the universe played out. So, how does the Alcubierre drive use this pliable nature of spacetime to achieve faster-than-light travel? The mechanism is both incredibly clever and, honestly, wonderfully simple in its basic concept. It doesn't propel a ship through space. Instead, it moves a bubble of space that contains the ship. The drive would create a highly specific and energetic distortion in the space-time fabric. It would cause the space-time directly in front of the ship to contract violently, pulling it together like an accordion. At the very same moment, it would cause the space-time immediately behind the ship to expand just as dramatically, pushing it apart. The ship itself would be enclosed within this disturbance, riding it like a surfer on an ocean wave. This moving region of compressed and expanded space-time is the famous warp bubble. One of the most appealing aspects of the Alcubierre drive is what it would feel like for the passengers inside the ship. Conventional methods of reaching near light speeds would involve immense and prolonged acceleration. The G-forces would be tremendous, likely fatal to any human crew. The most significant and daunting obstacle standing between us and a working Alcubierre drive is the need for a truly bizarre ingredient exotic matter. Now, this isn't just a rare or difficult to manufacture material. It's actually a form of matter with properties that seem to defy common sense and the known laws of physics. Alcubierre's own calculations showed that to create the required space-time curvature, especially the expansion of space behind the ship, you would need a region of negative energy density. In simple terms, you would need matter that has negative mass. If you were to hold a lump of it and push it, it would accelerate towards you instead of away from you. Even if we were to discover a way to create exotic matter, the second major hurdle emerges, the colossal energy requirement. The initial calculations performed by Miguel Alcubierre and others who followed up on his work painted a truly mind-boggling picture. To create a warp bubble large enough to contain a small starship, the amount of negative energy needed was staggering. Early estimates suggested you would need an amount of negative energy equivalent to the entire mass energy of the planet Jupiter. For decades, the Alcubierre drive was little more than a fascinating thought experiment, a set of equations on a blackboard. It was a beautiful piece of theoretical physics, but it seemed destined to remain just that, a theory. However, in recent years, a subtle but important shift has occurred. A small but dedicated community of physicists and engineers has begun to take the concept seriously, moving it from the pages of scientific journals into the controlled environment of the laboratory. This isn't a race to build a full-scale starship, of course. The challenges of exotic matter and immense energy are still far beyond us. Instead, this is a new kind of space race, one fought with laser beams, vacuum chambers, and sensitive detectors. Perhaps the most well-known effort to experimentally investigate the Alcubierre drive came from a NASA research group known as the Advanced Propulsion Physics Laboratory, or EagleWorks. Led by physicist Harold Sonny White, this small team at the Johnson Space Center set out to do what many thought was impossible, to build an experiment that could generate and detect a microscopic instance of a warp field, and their work centered around a device called the White-Juday Warp Field Interferometer. The connection between the Alcubierre drive and science fiction isn't just a passing similarity, it's a direct line of inspiration. The drive is, in many ways, the scientific child of Star Trek. As we've learned, Miguel Alcubierre was explicitly trying to create a mathematical framework for the warp drive he saw on the television show. We began this journey by looking up at the night sky, feeling the ancient human longing to reach for the stars. This dream, woven into our art, our stories, and our science, represents one of our most profound aspirations: to explore the unknown and expand the horizons of our world. The Alcubierre drive, born from the fusion of science fiction fantasy and rigorous physics, stands as the most compelling theoretical pathway to fulfilling that dream. The journey from a theoretical concept to a working starship is, however, fraught with challenges that are almost as vast as the distances we hope to cross. The need for exotic matter with negative energy density remains the great wall standing between us and the stars. The colossal energy requirements, even with the most optimistic theoretical refinements, demand a mastery of energy production that is centuries, if not millennia, beyond our current grasp. Yet despite these monumental obstacles, the pursuit of this knowledge is not a futile endeavor. The research into the Alcubierre drive, even in its earliest, most tentative stages, pushes the boundaries of our understanding. Ultimately, the Alcubierre drive is more than just a piece of speculative technology. It's a symbol of our unyielding hope and our relentless curiosity. It represents the idea that humanity is not destined to remain confined to this single, fragile planet. It offers a vision of a future where our descendants might walk on worlds orbiting other suns, where our civilization becomes a part of a larger galactic community. The path is long, and the challenges are immense. But the dream of the stars is a powerful one. It's the dream of our future, a destiny that calls to us from across the void, just waiting for us to find a way to answer.